Hello everyone, I'm Weima and I'm from University of Luxembourg. Today I will present our work test selection for deep learning system. The article is published in Traon. This work targeted to select the good data for deep learning system. In this article, we focus on the problem of selecting test input. In deep learning, test input selection is to select a subset of unlabeled data that should label to discover fault in deep learning models. Fault means the misclassification in our context. It is known that deep learning is not safe. Adversary attacking permutates the input by adding noise to flip the result. Usually, we expect that we can use adversary data to train and test the model. Every day, there are a lot of new data, and how to select the data for the deep learning model is very challenging. Some selection metrics are proposed to select the data. There are some design selection metrics to select data for the deep learning model. The first one is the news coverage. It depends on the proportion of active news. It has multiple different versions of the news coverage. The second is the surprise matrix. The type of the method measures the distance or density in the future space. The last one is uncertainty matrix. The type of the method introduces the randomness to the model and see how the model output change. The select data are those that have the highest uncertainty, surprise, or news coverage. News coverage counts the proportion of the active news. The value of the news is more than one threshold. We consider 5 variants of news coverage. News coverage is the basic one, the proportion of the active news that are more than one threshold. Additional news coverage always prefer the news that are never covered. The other variant of news coverage definition can be found in our paper. Surprise matrix is to measure if the data are far away from the cluster. For example, we have 3 clusters, yellow, red, and blue. The triangle data point belongs to the yellow cluster but is quite close to the red cluster. We consider 3 methods: likelihood-based surprise adequacy, it measures density. The second one is the distance-based surprise adequacy, it measures the distance. The last one is the silhouette coefficient, it measures the cluster consistency. We expect the surprise matrix can select the triangle data point. Uncertainty matrix introduces the randomness to the model and then observe the model output change. The most common way is to introduce the randomness by inserting dropout layers. Uncertainty matrix selects the data that are out of the probability distribution. In the work, we consider 4 methods. At first, we use the direct output probability, the maximum probability as one score. The second is to use the variance of the probability. The third is to use the maximum probability to weight the variance. We combine the first way and the second way. The last one is to use the KL method to measure the distribution change. The table summarizes the dataset, the model, and the model size, and the model optimizer we use. The last column is the validation accuracy of each model. In our work, we consider 3 datasets: MNIST, Fashion MNIST, and C14. MNIST is a handwriting dataset. Fashion MNIST is the same size with MNIST. C14 is an object classification dataset with 10 classes. We use 5 models: MLP, LearnNet, Modified MLP with modules, NetInNet, and VJJT. To craft the adversary data, we use 5 adversary data generation algorithms. The table shows the algorithm we use in our work. In our work, we have 2 research questions. The first research question is how can we select data to challenge a deep learning model by triggering misclassification. For this research question, we have 2 sub-research questions. We compute the conduct correlation between misclassification and the test selection score. For the first sub-research question, we consider test selection only uses the real data. For the second sub-research question, we also consider use the intermediate adversary measures and the final adversary measures from the attacking algorithm. We mix the real data and adversary data and then compute the correlation. We also mix the intermediate adversary data and the final adversary data. The intermediate adversary measures are still correctly classified, but the final adversary measures are misclassified. Conduct correlation is computed between the test matrix score and the misclassification label. The second research question is how to select the additional training data to improve the model performance. The table shows the result of the test selection with the real data. We compute the conduct correlation between misclassification and the selection matrix score on the original test data. The green part is uncertainty matrix, the orange part is the surprise adequacy matrix, and the yellow part is the new coverage matrix. We can see that KL and MaxP have the strongest correlation. We also mix the real data and the adversarial data. The head map shows the conduct correlation between misclassification and the matrix on a mix of real and adversary data using 5 different algorithms. The lighter the color, the better. Gray part in additional new coverage correspond to no increase in new coverage. The two figures are for DF and beam attacking algorithm, and we can see that MXP is better than the others. The two figures are for GSM and CW algorithm result. We can get the same conclusion. The figure is for FGSM. We can summarize that uncertainty and surprise-based metrics can discriminate well-classified real inputs from all real and adversary misclassified input. Overall, MaxP reaches the strongest correlation between 0.64 and 0.78. We also mix the intermediate image and the final adversary image from CW and FGSM attacking algorithm. The intermediate images are from the attacking process, and they are still classified correctly by the model. The table demonstrates the conduct correlation between miscalculation and the matrix score. We can, when consider FGSM, the correlation are similar to the situation when mix real data with adversary data. However, in the case of CW, they get weaker, although they remain medium to strong correlation for some metrics. In particular, the correlation of KL decrease, although this metrics perform well in the previous experience. It can be explained that CW is known to generate similar perturbation than the other adversary algorithm. Thus, the difference between the intermediate image and the final adversary image are smaller than FGSM. When we only consider the adversary input, the test selection metrics lose part of their capability. This is due to the inherent noise introduced by the adversary generation algorithm. MaxP still achieves the strongest correlation overall. For the second research question retraining, we randomly split the original training set into an initial training set and a candidate set that contains the remaining image. The test set remains untouched. In the first round, we train the model using only the initial training set and compute its accuracy on the test set. After finish training, we use the best model that we get to compute the test selection matrix on the remaining candidate set. Then we add the selection set from the candidate set to the current training set. We retrain the model from scratch using the whole augmented training set. The process is repeated until the candidate set is empty. The axis denotes the size of the training set at each iteration. Y-axis shows the average accuracy over 3 repetitions. Each subfigure represents one model retraining process using one dataset. The last two figures we use C14 and to retrain net and VGD10. We can see that new coverage cannot benefit the retraining, but uncertainty and surprise matrix can benefit the retraining. Thanks. Now you can ask me any question you want. Thank you.
Okay, welcome to the session Deep Neural Networks Data Selection. So we are in the live Q&A for the first paper of this session, Test Selection for Deep Learning Systems. It's a journal first paper, and Wei Ma is here to answer your questions. We already have some questions coming from the audience, so thank you very much. Wei, shall we start with the first one?
Okay.
Yeah, so they are congratulating you. You have demonstrated your strategy for deep learning systems that take images as input. Could you comment on its applicability for other kinds of deep learning systems?
I think the answer is yes, and you can apply this test matrix to the other kind of deep learning system. Because, for example, for the in our experiments, we consider the classification of deep learning system. Actually, if you think about the system, in the end, everything is output the values. And the difference is the last deep learning model layer. If for classification, it's maybe you need a software mix. as the decision layer. And but if the regression task maybe it's the linear layer or the other active function you want to use. And I think there's there's no so much difference, but of course you should adapt the test task. And I think it's not difficult if you think of them just the numerical values. Yeah.
Okay. So the second question is from David. He again thanks you for the great talk. The question is, do your results provide any insights for how to design better test selection criteria or metrics?
I think to design the better test selection criteria or metrics, I think you should consider your test should challenge the deep learning model or system, and it should first the test criteria should select the data, and the data should represent the training data set, because it's like it's like a regression testing, and you need to make sure the model can work for the training data set. So first, your test selection should select the data. These data are similar with the training data set. Make sure they have the same data distribution. And the second one, to challenge the model, your test selection criteria or metrics should focus on the corner cases of the data. So I mean, many misclassification images or adversary example, if you say that will become the common input to that will put the common input to the corner cases. So in my understanding, we should focus on the two things. Your test metrics should select the similar data distribution with your training data set. Make sure your model can work for the training data set. It's like regression testing. Second, your test selection should focus on the corner cases so that it can challenge your model and it give you some insight to improve your model performance or security, like that. Yeah.
Okay. I hope the answer is sufficient for the question.
Sorry.
No problem. So I have a question. So in your paper, there's a, please correct me if I'm wrong. As far as I understand, when you have adversarial inputs, you conclude that test selection metrics lose their capability to check the success of the deep learning systems. Is that right?
I get your point. Because when we say about the concurring, we use the intermediate adversary images. So that for these images, the model also can classify them correctly. So, and in that cases, in this scenario, the test metrics will lose their power. But if you consider the final adversary images, I mean, the final adversary image means in the end, the model will misclassify this adversary example. You will see actually the test metrics can give very strong power. For example, if you check the correlation, when we consider the intermediate adversary images, this image model also can classify them correctly. The correlation get weaker. But if you if you mix the real image and the final adversary misclassified images, you will see the correlation get very strong. So I think it's because for the adversary taking, they just optimize from the common input to the adversary example to find the corner cases to trigger the input. I think it's my conclusion. Yeah.
Okay. While waiting for the other questions, maybe I can ask another one. Okay. Normally, when we are evaluating the test set its effectiveness. Like we use these simple, well-known coverage values, coverage metrics, just like you also have in this study. Also, we have this mutation score concept. Probably you are also aware. So this mutation testing, and for me, this using this adversarial attacks look like this mutation testing concept. Can you also give your opinion about this? Like, because in mutation testing also you have these mutant source codes which has injected bugs in it, and then test cases are checked whether they are able to find those mutants. So
Yeah.
can we find a resemblance between that and the adversarial attacks data in this case?
I think we can generalize the mutation concept to the deep learning system. I think there are many works support that. And I think for the adversarial example, it's like phasing, because you change the input, you doesn't change the model. Because for mutation testing, usually you change the code and given the input, you will try to see if the changed code is killed, with a mutant is killed or still survive. And but for the adversarial attacking, usually that will change the input and protect the pixel values. And it's just give us very small noise, and then to fill the system. And yeah.
Thank you. There are questions, so I would like to read them to you. One question from Tien. Did you come up with your testing criteria metrics from intuition or learning from data? If they are from intuition, did you find other interesting selection criteria from your empirical results? I think he is mentioning about the testing metrics that you use, like different coverage values.
Okay, from the intuition or learning from data, I think it. I mean, if you follow machine learning, it is a statistical learning. Given your data, it will learn everything from the data. So it's like if you see, it's like a data distribution. So all all the test criteria metrics is also like a statistical method to see the fixed patterns for your model. So I think I get these test criteria metrics are from the learning, from the data. Everything is about data distribution, and
we have one more question and a little bit time left. So whether he asks whether the test metric can be used to discriminate normal data and adversarial data.
Yeah, the answer is yes. Actually, we have some actual experiments. We use these output from these test metrics as the features to detect the normal data and adversarial data. The results are quite good. It's quite, but we don't put them to the paper because we focus on test selection, not detect the adversarial example. Actually, the result is